Here is Yuri Oku from Osaka University,
Yes.
so the floor is yours. And you have 15 minutes. And
Yes. Okay.
5 minutes.
Thank you. Hi, I'm Yuri Oku from Osaka University, Japan. And I first would like to thank organizer for giving me time to talk. So I'm second year PhD student in 3-year PhD course. And so today I talk about this paper, and this is a collaboration work with these collaborators. And I'm happy I can talk on this. Thank you. On this paper today, because this paper is just published today. Okay. And so this is a bit detailed outline of this talk. So yeah, so I first start from basic point of why we need supernova feedback model, and what do we need to model. And next I talk about our super bubble simulation. So I simulate momentum of I study momentum of super bubble using high resolution Athena simulation, and I'll talk about how to apply the result to galaxy feedback model for galaxy simulation. And I also talk about the thermal feedback model and how to implement in SPH simulation. And finally, I'll show a test simulation using isolated galaxy initial condition by Agora project. Okay, so it's a well-known problem that in galaxy simulation, the resolution is low, so we can resolve self-Taylor phase. So this is a criterion we need to resolve self-Taylor phase in of supernova remnant. And so here I consider the case of SPH. So in case of SPH, resolution is like this, and this RSF is called shell formation radius. I will discuss later. So input this value to this equation, then we get this value. And this is less than 10 solar mass, so we can see that it's almost impossible to run a resolved simulation of a Milky Way mass galaxy with currently available computational facilities. So this is a numerical experiment by Fu 19. So they use gadget-3 simulation and showing that this momentum of supernova remnant converges at 1 solar mass, so consistent with this estimation. Okay, so we need feedback model, and so here I consider two modes of supernova feedback. How supernova feedback works on galaxy formation evolution. And so the first is kinetic feedback. So after supernova explosion, supernova remnants form and inject momentum to surrounding ISM. And this momentum drives turbulence in ISM. And so this hot bubble grows and sometimes break out from galaxy and then produce hot outflow. This is important. So in galaxy CGM connection, and also this hot outflow carries metals out from galaxy to CGM. So in this work, we develop model considering both these kinetic and thermal feedback modes, and a model based on high resolution simulations. So I want to start from this analytic theory of a supernova remnant. So this is a simplified picture of how supernova remnant grows in time. So so supernova remnant grows in 4 steps. First is free expansion phase, where the increase of mass is negligible, so energy and momentum is conserved. And then enter self-Taylor phase, where the energy is conserved but mass increases and the momentum also increases rapidly. And in this phase, about 80% of the terminal momentum is acquired until this shell formation time. And this shell formation time can be estimated like this. So the shell formation time is the minimum value of T shock and T cool, where this T shock is the time when the ISM is shocked by the blast wave. And here T cool is cooling time, and cooling time is this. And here is lambda is a cooling function. And this cooling function can be approximated like this. So this is a cooling function with different metallicities. And here is a metallicity dependent enters. So so I fit this cooling functions with this fitting function, and to obtain the metallicity dependent shell formation time. So for SNR formed by single supernova, this shell formation time is this. And for superbubble formed by multiple supernova, then the dependence on the time interval of each supernova enters, then and the shell formation time becomes like this. Okay, so that's the basic analytics theory. So here I show my numerical experiment using Asena++ code. We run 36 simulations changing density and metallicity and time interval of supernova. And we inject thermal energy 10 times into at the center of this simulation box. And this movie shows the density and temperature of superbubble. You can see that the bubbles are growing. And so we run 36 simulations and obtain the time evolution of radius and momentum of superbubbles. This left panel showing the radius and the right panel is momentum. And these panels, the x and y axis are normalized by shell formation time and the radius and momentum at shell formation time. So then we can obtain this universal scaling relation. So until this shell formation time, the superbubble grows adiabatically and then enters the radiative phase. And so, in this time evolution of radius, then the scaling is t to the 1 over 2. And for momentum, the momentum grows t to the 7 over 5 until this shell formation time. And then after that, the momentum grows linearly. And so we obtain this fitting function, and we will apply these functions to supernova field model for galaxy simulation. But as I explained, these shell formation time have dependence on time interval of supernova. So here I consider how to apply the results to galaxy simulation, because in galaxy simulation we don't resolve each stars, and we have the same masses of star particles. So I consider a picture like this. So in reality, different size of star cluster forms and different size of super bubbles will formed. And the size of star cluster follows the initial star cluster mass function. And assuming that each star cluster has the same initial mass function, then the number function of supernova is also has the same form. And then we can average momentum of superbubble per supernova by integrating by this integration. And we will finally obtain this average momentum per supernova. And interestingly, the dependence on density is very small, and this lambda term shows the dependence on metallicity. Thank you. There are factor 3 enhancement of momentum in zero metallicity environment than solar metallicity, because in zero metallicity environment, the cooling time is longer, so the more momentum is acquired in adiabatic phase. And next I briefly talk about stochastic thermal feedback model. So we developed a stochastic thermal feedback model based on Dirac-Becker-Sayer's model, but we use entropy as a parameter. So there is a well-known problem called overcooling problem. So if we simply distribute thermal energy from supernova, then the energy is small compared to the particle mass, so we cannot heat up particle to high enough temperature and then cool down again. So by using stochastic method, we can heat up to high temperature and produce hot outflow. So I here summarize how I implement the models to our code. So for mechanical kinetic feedback, we assign momentum to neighbor particle, so like this. So in SPH, there are star and surrounding gas particle. So I use a Voronoi tessellation on surface of the sphere and assign each particle, assign momentum to each particle weighted by this solid angle omega. And so as I explained, thermal feedback is stochastic model. And so I implement the model to Galaxy Osaka code and run isolated galaxy simulation. And we use IC from Agora compression and added hot gas halo following Shin et al. So here I compare 5 cases and change turning on and off each feedback mode. So this is fiduciary case, having both kinetic and thermal feedback. And this is only kinetic and only thermal and no feedback case. And this triangle means we inject thermal energy, but not stochastic. And so this top is density and temperature and metallicity. And in these 2 cases with stochastic thermal feedback, we can see bright points for hot bubble formed by stochastic thermal feedback. And in these 2 cases without kinetic feedback, the galactic disk becomes clumpy, and so this suggests that the kinetic feedback drive turbulence and support galactic disk against gravitational instability. And this is a star formation rate, and comparing 5 lines, and you can see that these 3 lines with kinetic feedback have a smaller star formation rate. So the kinetic feedback suppresses star formation, while the stochastic thermal feedback suppresses star formation only weakly. And this movie shows a metal column density from edge on view, and this is a biliar radius scale. So you can clearly see that these 2 cases with stochastic thermal feedback, we can see metal outflow reaching biliar radius scale. And in this fiduciary case, the mass loading factor was 0.3 and the wind velocity was 500 km per second at this biliar radius. Okay, so this is summary. So we developed a supernova feedback model based on high-resolution simulation, and show that the kinetic feedback suppress star formation, while thermal feedback drive hot outflow and transport metal to CGM. And now I'm porting this model to Gadgets for Osaka, Gadgets for code. And our next step is to use this model in realistic cosmological simulation and compare with observation. Thank you.
I have a question regarding your momentum injection. So it has been shown by Eric Gentry and collaborators that while one-dimensional simulations of momentum injected by supernova yields some result, when you go to 3D, the results are widely unconvergent, and you can get a very wide range of momenta injected when you have clustered supernovae. I was wondering if you tried, because you used only one value, if I remember correctly, if you try to vary this and how this affects your results.
Yeah. So yes. So the momentum of supernovae depends on numerical method and dimensionality, and so I forgot, but so it's a bit due to the so in one-dimensional simulation, the mixing between shell and in hot gas is not considered. So here we use a 3D grid called Athena++ to include the mixing effect. So I think the and our result is consistent with the previous work by Kim and Stryker. So yeah, so is it answer to your question?
I was asking if you try to vary because the momentum in 3D found a very wide range of values, all of minute difference, and I was wondering if you try to vary the amount of momentum and see how it gets the result.
So sorry, discuss later. Thank you.
So I may have missed it. Did you also measure the energy and momentum loading factors of your winds?
In galaxy simulation.
Yeah, in your...
Yes, we measured. So I think I have. Yeah, so.
Oh, okay, thank you.
Yeah. This is mass loading factor, energy loading factor, metal loading factor, and outflow velocity. And yeah, so so for example, in this, and showing the for each phases, and here we slightly see that with kinetic feedback, the mass loading factor at this and here is larger than the case without kinetic field. Thank you.
Okay, unless there is a quick question, I think, no, yes. I think we can thank the speaker again. And so it's lunchtime, and I think we reconvene at 2:05.